Okay, let us move on to the next topic in electromagnetic induction. So the next topic is motional EMF by Lorentz force. So even here we are having the same figure here. So let us consider a conductor PQRS, and PQ is the movable part of the conductor. So PQ part of the conductor will move with the velocity V, and the length of the conductor is L. The length of the conductor PQ is L. So the PQ conductor is at a distance x from SR. So these are the basic things which we need to know in this one. So let Q be the arbitrary charge that is present in here. Okay, let Q be the any arbitrary charge. It could be any charge. Okay, so let us have this Q here. So let us take the Lorentz force here. Let us consider the Lorentz force here. Okay, so we need to know what Lorentz force is. So it is the sum of electrical force. So QE plus the sum of electrical force plus magnetic force QVB sine theta. So this is the electric force and magnetic force. So the sum of electrical force and magnetic force is equal to Lorentz force here. So since there is no presence of electric field here or electrical force here, we shall neglect this electrical force. So that is E is equal to 0. So this term will be equal to 0 here. So QVB sine theta. Okay, then so here theta is equal to 90 degree here, because V and magnetic field B, they are perpendicular to each other. V and B are perpendicular to each other. So F is equal to QVB into sine 90 degree. So F is equal to QVB, sine time is 1. So F will be equal to QVB here. Then next we shall take the work done here. Work done is equal to force into displacement. Work done is given by force into displacement. So we have force here, that is equal to F is equal to Q V B, and the displacement is L here. So L should be taken as the displacement here. So then work done by this, let us put this Q to the, let us take this Q to the left hand side. Work done by charge is equal to VBL. So work done by charge or W by Q is equal to EM. So it is equal to EMF. Work done by charge is always equal to EMF, that is E here. So E will be equal to BLV. So this is the expression for motional EMF by the Lorentz force. We have taken Lorentz force here. So the same expression we get here. So even in the motional EMF also we got the same expression. Even here we will get the same expression by using the Lorentz force here. That is F is equal to QE plus QVB sine theta. I'll repeat again that the Lorentz force is the sum of electrical force plus electrical force and magnetic force. Okay, it is the sum of electrical force and magnetic force here. Okay, the next topic is a quantitative study of Lenz's law or energy consideration. How does the energy behave in here? So the same figure it is. So let us consider a conductor, rectangular conductor PQRS. So let PQ be the movable part of the conductor which moves with the velocity v. Let L be the length of the conductor. Let x be the distance between PQ and RS. Let I be the current that is flowing through this conductor PQRS. So then the current I is given by E by R. So R is the negligible amount of resistance that is present here. So E is the EMF here, I is the current here, I is equal to E by R. So we all know the expression of E here. E is equal to BLV. So E is equal to BLV. Let us substitute this E upon this equation. So I is equal to BLV by R. So now we shall take a force. So we shall write the expression for force. The force required to move the conductor PQ. The force required to move the movable part of the conductor PQ. That is given by F is equal to BIL sin theta. So this is the expression for force that is required to move this movable part of the conductor PQ that moves with the velocity v here. Now the theta, the value of theta is 90 degree here. Since the velocity v and magnetic field B, they are perpendicular to each other, the angle theta is equal to 90 degree. So F is equal to BIL degree. So sin 90 is 1. So F is equal to BIL here. Let us substitute the equation I. Let us consider this as equation number 1 and this as equation number 2 here. Let us substitute this equation 1 to this equation 2 here. Now the force F is equal to B. I is BLV by R into L here. So F is equal to B square L square V by R. Okay, this is the expression for force here. Now we shall take the mechanical power. The expression for mechanical power to move this movable part of the conductor. So it is given by force into velocity. So power is given by force into velocity. So power is equal to force is this one, P square L square V by R into velocity is given by V here. So what happens now? Power is equal to P square L square V square divided by R. So this is the expression for mechanical power. Mechanical power to move the movable part of the conductor. So what happens here is the mechanical energy which is given by this expression V square L square V square by R. This mechanical energy is converted into electrical energy. The mechanical energy is converted into electrical energy. That is the current here. So the electrical energy is in turn converted into thermal energy here. So mechanical energy is converted into electrical energy and electrical energy is converted into thermal energy here. Thermal means heat energy here. So heat is liberated when energy is transformed from one form to another form here. So now let us write the expression for electrical power here. So that power is given by Pj. So what this J represents is, so the thermal energy or thermal heat energy which is liberated here, or the mechanical energy which is converted into electrical energy, and that electrical energy is converted into thermal energy or the heat energy. That heat energy is called as joule heat here. So that heat energy is called as Joule heat. That Joule heat is J here. That Joule heat is J here. So this electrical power is given by current into voltage. It is given by current into voltage. You will learn this in current electricity chapter. So current is I. So the expression for voltage is given by V is equal to I R. So here we have small internal resistance or small negligible resistance, that is R. So we are taking R itself. So P J is equal to I square R. Let us substitute the expression for I. So this one, the equation 1 onto this equation. So P J is equal to, what is the expression for I here? P L V by R whole square into R. So P J is equal to V square L square V square divided by R square into R. So here R and R they'll get cancelled. So electrical power Pj is equal to V square L square V square divided by R. So you can clearly observe here equation. Let us consider this as equation 3 and this as equation number 4. So you can clearly see here equation 3 and equation 4, they are same, they are similar. So this is mechanical power and this is electrical power. So mechanical power, I told you earlier itself, mechanical energy is converted into electrical energy and electrical energy is converted into thermal energy. So even the power also, this is mechanical power. Mechanical power is converted into electrical power and electrical power is converted into thermal power, thermal energy or thermal heat energy. So power is converted, mechanical power is converted into electrical power. So the expressions equation 3 and equation 4, they are similar here. So this is the quantitative study of Lenz's law or energy consideration, how the energy behaves in here. The next topic is eddy currents. Eddy currents are circulating currents when a bulk piece of conductor is made to oscillate between the magnets due to change in magnetic flux around it. So eddy currents are circulating currents like this. It will be circulating like this. These currents will be like this, circulating currents in the form of eddies or swirling eddies. These are like swirling eddies. So these type of currents will be formed when a bulk piece of conductor is made to oscillate between the magnets, and this current is formed due to change in magnetic flux that is linked with it. Okay, so eddy currents are circulating currents, or they are formed like in the form of eddies. Look, when you put a stone onto a pond, the water is formed. Water moves in the shape of like this. Ripples will be formed in the water. So now those ripples will move in the form of eddies. These are like swirling eddies. So even the current will flow like this itself. Like this it will flow. So this is the form it flows. Okay, the current will be formed, and this current is called as eddy current. So here a copper plate is used here. You can clearly see here the current here is moving in anti-clockwise direction, and here when the same copper plate comes here, the current is moving in anti-clockwise direction. Here it is clockwise and here it is anti-clockwise. So it is moving away, one is moving towards the magnet. So when it is oscillating to and fro here. So due to the Faraday's law of induction, so there will be opposition force to the flow of this current here, or it will oppose the magnetic flux here. So due to the opposition here, damping can be observed here. So this copper plate which is oscillating will gradually come to rest here. Okay, so these eddy currents, they have certain advantages as well as disadvantages. First, let us know about advantages here. So the first advantage is magnetic braking in train. So you might have observed in metro railway station. So this metro trains, they make use of this magnetic brakings. What they do is, people are made to stand at a particular point, and that on that particular point itself, the train will come to rest. So the doors will open and the people will enter the train there. You might have observed that. Okay, so that thing they use magnetic braking there. So what happens is, so this will be the railway track here. So this will be the wheels of the train here. So this railway trains, they will have huge magnets, so which will produce more amount of magnetic field here. Due to that magnetic field, since the wheel is moving here, there will be currents that is formed in this wheel. So those currents will be in the form of eddies here. Eddy currents will be formed. Okay, this currents will oppose. What it will oppose? It will oppose the magnetic flux here, which is formed. So here, because of this opposition, the wheel will slow down. So the wheel will gradually come to rest. So here, they make use of this eddy currents. So magnetic braking in trains, they make use of eddy currents. So the next one is electromagnetic dampening. So electromagnetic dampening is used in galvanometers. So galvanometers are used to measure or to detect small variable current that is present in the circuit. So this galvanometer, what it does is, it shows certain amount of reading. So after showing that reading, it should come to its initial position. So because of that, so it uses eddy currents for the opposition, and after that opposition itself, after showing certain amount of deflection, it will come to its rest position or its original position. So here, electromagnetic damping, they use this eddy currents. So the next one is induction furnace. Induction furnace, you might have learnt in your chemistry classes. So it's a kind of furnace where they use alternating current to a furnace. So alternating current will give more amount of heat. It will generate more amount of heat. That heat will burn, or it will heat the metallic things. Okay, all the two metals or two non-metals, or a metal with the non-metal is heated together. So they are heated together and they will be melted, and alloys are made in this induction furnace. So to make all alloys, we use this induction furnace. So this induction furnace will make use of eddy currents. So the next one is electric power meters. So in your houses, many of you might be having analogous power meters. So this analogous power meters, they'll have a circular disc which will be revolving, it will be rotating always. What it does is that it rotates because of eddy currents. So eddy currents will be formed. Because of that eddy currents, the circular disc will be moving. Okay, so this circular disc, how much it rotates, it gives meter is recorded because of this rotating disc. Upon that itself, you will get meter readings. Upon that itself, you will get electricity bill. So thus, electric power meters, they make use of eddy currents. So the next one is disadvantages, the next topic. So the first disadvantage of this is eddy currents is loss of electrical energy in the form of heat. So when in the metallic blocks, when this eddy currents they move, they are formed, what it happens is loss of electrical energy in the form of heat. There will be a lot of loss of, there will be a huge amount of loss in the form of heat. The electrical energy is lost in the form of heat here. So the heat energy cannot be used again sometimes. So this heat energy can be observed here. So this is not at all useful for us. So it is the biggest disadvantage of this eddy currents. Okay. The next one is break insulation used in electrical appliances. So in your house you might be using many appliances like fridge, washing machine, your grinder, mixer, your oven, everything. All these are electrical appliances. What it does is, what happens sometimes there will be a formation of eddy currents. Because of that formation of eddy currents, it will break the insulation that is used in this electrical appliances. Gradually, because of this breaks in insulation, the electrical appliances will stop working. So this is a disadvantage of eddy currents. So the next one is unwanted damping effect. So in certain appliances or certain electrical devices or electronic appliances, we observe this unwanted damping effect, which is not required. In the galvanometer electromagnetic damping, we require damping there. Because of that damping itself, the galvanometer will come to its original position or rest position. Okay, but in other appliances or other devices, electronic gadgets or electronic devices, we don't require this damping effect. Okay, we need them to work properly. So even there we can observe this damping effect. So it is not at all required. So even this is the biggest disadvantage in eddy currents.